Hello. So this time we'll have a rod, and this rod is of mass m and length L, and this rod is hinged at one point. I'm calling this point as O. So it is physically hinged at this point. So in the beginning, this rod was horizontally held. It was like we were holding it, this rod. And then suddenly we release this from rest. So at this instant, it is not moving, and later on it will move. Obviously, this rod is hinged at about this axis, so the movement of the rod will be happening like that, clockwise. G is acting downward, obviously. So when this rod will be moving, there are multiple things we will love to calculate. First thing is, what will be its angular acceleration or acceleration of the center of mass? What will be its velocity or angular velocity when it will be displaced by some angle? We will want to calculate when this rod will become vertical. At that time, what will be its velocity? So many things we will want to calculate in this case. Okay, but everything we'll calculate by calculating the alpha, angular acceleration. So let's do that. So this is the initial state, and obviously when this rod will be moving, its angle with the horizontal will keep changing. So to calculate such type of problem, what we do, we go for a general point. We don't take values of accelerations at specific points. What we do, we go for general points. So what I'll do, this is t0, initial state. So I'll go for t is equals to t state, which is a general state. This is t is equals to after some time. I'm looking at the rod. So when I look at the rod after some time, this rod obviously would have displaced by an angle theta. So some displacement has happened there. Okay, and at this instant, this rod will be having some angular acceleration, alpha we call it, and it will be having some angular speed as well. Okay, so to calculate alpha, obviously we will need to calculate the torque. I can select any axis, but as we know, I have told you earlier, whenever we have a physical hinge, that will always be our preference for the axis. So there is a hinge, physical hinge is there. So I'll assume my axis at the hinge itself. So if I assume my axis at the hinge itself, like if you say total number of forces which are acting here, obviously there is one mg which is acting, and obviously it is downward. Then there is this reaction force acting at this point. So if you see the reaction force, the direction of reaction force is generally not known. So for that, what we do, we divide this reaction force into two components. So I'm dividing it into nx and ny. So I have an equation, tau, obviously with respect to O, is equals to IO alpha. So torque is equals to I alpha. The axis for torque and the axis for moment of inertia has to be same, and alpha is completely independent of the axis. So whatever axis you calculate alpha with, alpha will be same with respect to each and every axis. So we know the formula for IO. So let's put the IO first. Moment of inertia for the rod about the end. We have a formula, and that formula is ml square by 3. Moment of inertia of the rod about the center of mass is ml square by 12. About one of the corner is ml square by 3. Then we will calculate the torque. About 0.2, obviously. So if I calculate the torque about 0.2, there are total 3 forces acting onto the body. One is nx, second is ny, and the third is mg. So you see, the axis nx and ny, both the forces are passing through the axis itself. So it will be 0 plus 0. Torque will be 0. Now, if you go for the mg, calculation of torque because of mg, so we have 3 methods. Either we go for f sine theta, or we have one more method. Generally, we prefer that. We extend the force. If we extend the force, and then we put the perpendicular from the axis onto this extension. So this is the perpendicular. So the value of torque will be equals to magnitude of force multiplied with perpendicular component of r. This is the perpendicular component of r. So obviously this length is L by 2. Midpoint. And this angle is theta. So this r, perpendicular component of r, will be equals to L by 2 cos theta. We can put the value. L by 2 cos theta, and that becomes the value for magnitude of torque. Now to calculate the direction, left hand axis, right hand force. Let's move the force. So it's clockwise. We put the values there. The value of torque mgl by 2 cos theta, that is clockwise direction, is equals to ml square by 3 into alpha. Direction of alpha and the direction here for the torque will be same. Okay, so now you can see we can cancel out so many things. M and M gets cancelled out. L cancelled one thing. So the alpha becomes 3g by 2 cos theta and torque wise. So if you see the value of alpha, this alpha is not constant. The value of alpha depends upon the theta. So as the value of theta will keep changing, the value of alpha will also keep changing. Okay. So alpha comes out to be a variable. So once we calculate alpha, if you want to calculate omega, since alpha is not a constant, to calculate omega, we will have to go for the differential equation. So differential relationship between alpha and omega, if you remember, alpha is nothing but omega, magnitude of alpha is nothing but omega d omega by d theta. There is other relations also like d omega by dt also, but the thing is if you see the alpha, it depends upon theta. So I want to use a differential equation which should have the alpha, omega and theta because I already have the relationship of alpha with respect to theta. So I'll use this differential equation. This differential equation between angular acceleration and angular velocity. Let's put the values. So it is 3g by 2 cos theta. That's the value of alpha. And that will be equals to omega d omega by d theta. So that will be omega d omega. Let's separate the variable. We are separating the variables, omega on one side. And then it will be 3g by 2 cos theta d theta. So this is our differential equation. Let's integrate this equation. If I do integration, we will have to put the limits also. So limit, if you see, the theta is varying from 0. So lower limit of theta is 0. So when the theta was 0, what will be the value of omega? It was 0. Upper limit, I will not go for extreme value. I will go for general value for upper limit because I am interested in the relationship, just like this one. So upper limit I am taking as theta, and here also I am taking as omega. It's a variable, it's also a variable. So let's integrate this. So if I do the integration, cos theta d theta, the integration is sin theta. Limits from 0 to theta. And the integration of omega d omega is omega square by 2. Limits from 0 to omega. And we put the values, omega square by 2 minus 0 is equals to 3g by 2 sin theta minus sin 0. And sin 0 is 0. So omega square by 2 becomes 3g by 2 sin theta. 2 and 2 gets cancelled out. And omega becomes magnitude wise 3g sin theta. And if you see the direction of alpha and omega, if you see it's same. The direction of omega, this alpha is increasing. So if I want this is the magnitude of omega. But if I want the relation omega in terms of vector, it will be 3g sin theta, and direction I will show as clockwise. And clockwise is inside direction. So whatever direction you are taking inside, whether it is x-axis, y-axis or z-axis, in this direction, whatever direction you are taking, you will put the unit vector in this direction in place of this. Okay. So that's how we calculate alpha and omega if there is a rigid body and which is fixed, which is moving actually. So general relation, just as we used to do in case of laws of motion. But there we used to deal with point masses. When there is a rigid body, again we go for general points. At general points, there we used to make the FBD. Here we are making the torque body diagram. So when we are balancing the torque from this, we are getting the alpha, and by the look of alpha, if alpha is variable, we have to go for differential equation. If the alpha is a constant, we do have a kinematical relationships. Okay. So I hope you understand this. Thank you.